Hello, good day, good morning, good afternoon, good evening, depending on wherever you are. I'm Dr. Oslin Oluwaseun Ogundokun from Swanee University of Technology. I'm a postdoc researcher there, and I'm here to make a presentation on the topic SHAP-Optimized Ensemble Learning Framework for Cattle Retinal Disease Classification using PCA-Transformed RGB imaging. And I have a co-author of Dr. Bello, Professor Pius, and the rest. These are my presentation outline. I'll be going through from background and motivation, research gap, objective, contribution, dataset and preprocessing, methodology, overview, baseline versus optimized model, result, comparative performance, clinical and practical implication, limitation, conclusion, and references. So as a form of background, over the years, it has been discovered that retinal imaging is a non-invasive diagnostic tool in veterinary medicine, and it has helped to detect ocular and semantic condition in cattle. But it has been discovered that we have a few automated systems that are available for livestock disease detection. And this led to us being motivated to propose a lightweight, interpretable AI tool for deployment. Then it was also discovered that deep learning is accurate, but computationally it is heavy and incomprehensible. And we noticed that we have classical examples which has been effective, but they are often under optimized. And explainability, we discovered that it is very critical and can be used in veterinary adoption. And it was discovered while we were researching that there are limited researches which have combined grid search optimization with sharp interpretability. Now, the objective of this study is we have four objectives. One was to develop a robust interpretable assembled pipeline, compare the baseline with the optimized assembles, and then we use the SHAP for transparency in future contribution, and then we try to validate with real-world cattle retinal database available on cargo repository. The main contribution of this study was one that we used the grid search CV optimized assembled, which combine the random forest model, the gradient boosting model, and also extra tree model. Then we also use PCA-Transformed GRB features for dimensionality reduction, and then we use shape-based interpretability which was integrated into the workflow, and then deployable lightweight veterinary diagnostic was also contributed in this study. The data set was initially downloaded from a cargo repository, and it initially had a two binary, and that is two classes, which is the binary classification, which had it was labeled as a CVD versus non-CVD. So we relabel it to LD versus non-LD cattle retina. Then we process by resizing the images into 128 by 128, and then we normalize to RGB and we flatten before going through the training process. The data set was splitted into three, 80% training, 10% validation, 10% test using the stratified split. And then the PCA was reduced from 49,152 features to 150 features. Then the methodology involved the preprocessing model, the example model, the grid search and CV optimization, and also the SHAP that was introduced for feature explainability. Then this is the proposed model, the architecture of our proposed system We input our retinal images, we process the image, we pass it through the PCA to reduce the dimensionality reduction, to carry out dimensionality reduction, and then we assemble each of our models. Then we use the grid search optimization on it, and we train our model. We introduce our SHAP explainability. Trying to compare the baseline with optimized model, it was discovered that we optimized using the grid search CV, like I said earlier, and then it was discovered that the proposed model showed better sensitivity and precision during the evaluation of the model. This is the result that was gotten from the training. These are confusion metrics. And if you see the confusion metrics, the example is by the left, optimized model. That is the example model. And then for the optimized model is by the right. That's the way I'm sitting. And it was discovered that the correct classification was 24 LD retina, cattle retina over the example model that gave 19 LD cattle retina. So this is a proof that the optimized model actually performed better than the ordinary assembled model, which did not introduce the use of grid search. Also, in our ROC, here you see it was discovered that the ROC had 0.73 over the baseline model, which had 0.68. Then in comparison, it was discovered that the proposed model, the optimized model, had better results over the baseline model in terms of accuracy, AUC, and other metrics. So the accuracy was 76.5 over 73.0 for baseline, and then AUC of 0.73 over 0.68 for baseline model. Then this is our SHAP explainability, and from the image it was discovered that this image gave the top pieces, and that they had a moderate and consistent influence, and this also helped to improve the trust and transparency in decision. So the clinical and practical implication of this study is that early retinal disease detection gives timely intervention for these cattle. And then we also introduced the use of lightweight model, which allows for deployment in farms and rural clinic, and the introduction of the SHAP ensure interpretability in veterinaries. But the limitation of this study is that we only use binary classification, and also there were misclassification which were persistent in the LD class, and the PCA-based model where features are less clinical interpretable. So in conclusion, we developed a SHAP-optimized assembled framework for cattle retinal disease classification, and along the line to optimize the model, we integrated the use of PCA feature reduction with the model that was optimized with grid search CV, and this achieved an improved accuracy of 76.5% and AUC of 0.73%, and also with our proposed model, we're able to reduce the false positive and false negative, which enhance diagnostic reliability, and we're able to introduce SHAP explainability to provide transparency and also increase trust in AI-assisted veterinary screening. We also introduced the use of lightweight model, which make it deployable in farm and rural veterinary setting. But in the future, we propose that we extend the study by using multi-class retinal disease for diagnosis, and then we propose to use multimodal image also in our future work. These are some of our references, and thank you for your attention. If you have questions, since I'm presenting, since this is a pre-recorded presentation, these are my contacts. You can message me or send, this is my WhatsApp number, send a WhatsApp number or message me through email. If you have questions, then I can answer. And thank you very much for listening and for the opportunity to make this presentation. Thank you once again.